consultant in AWS Pro GCC India. So, in this presentation, we are going to talk about optimization of procedural language Postgres performance use cases. So, basically, right. So, the agenda first, we will go through the procedural language word conversion overview. So, basically, take a step back and we understand why we need procedural language. And then we go through the use cases. Like first one on the parallelism, second one on the CPU study, and third one on the R contribution. And then we talk about the new feature which got released in Postgres 15 multivariate statistics, followed by question and answers. So right, so procedural language, right? So why we are going for procedural language? Yeah. So the first one is the basic, right? So procedural language which combines a group of competition statements and SQL queries, right? So why we get the advantage, right? So in procedural language, you can combine multiple SQL queries and send back to the database server, by which you get an advantage of network overhead, memory, and query passing. So consider an example. So a simple these statements. For the first one is hitting the data, and second one is consuming, and third one you are getting some condition and return back the results. Assume you could see that three SQLs are independently hitting from client to server. So every time it involves network overhead, and there is a memory. So if you combine all these three SQLs in a procedure, then you are sending all together one time to database server. You are avoiding 3 times network overhead, and query passing also not needed every time. So the performance. So when we look at the performance, right, as a DBR developer, so we mostly jump into the SQL queries, which is obvious, right? So in this talk, I want to present a perspective that not only SQL tuning, so why can't we look into the deep dive on the application logic or procedure code? So you can look into the return types, you can look into the options available like parallelism, and you can see that how the looping is organized and what the function call is happening there. These are all, you can deep dive and you can tune, you can get the performance benefit. For example, in a procedure, right, if you have frequent bit of the same data like temporary table or dynamical set, right? So why can't you build a temporary table and make use of that? So again, right, if you think of a temporary table, I just said, right, memory is the key. You need to pass on how much you are loading into the using the temporary table. The first use case. So the first use case, applying parallelism at the function level, right? So to apply the parallelism at the function level, first we need to understand what context I am trying to write. So the application context which we have tuned, right? So it's an equity application, it's a financial application, right? So obviously performance is critical. And the workload, so the function has to be executed, within 1 second, and there are such 50,000 API calls in the production workload. And for this equity application, the business logic is coded in the procedural language. So basically, you are calling a procedure certain parameters that are running the business logic and sending back the queries to the environment. And it's typically transactional data, and 1 terabyte active data is there. So to apply parallelism, right, we cannot apply all, right? So there should be certain criteria. So applying parallelism means you are making the multi-threading, right? So in our financial application, we have adequate CPU available. So we choose certain functions for this parallelism to get the advantage. And which functions which you can choose, right? So basically, if your application is running on large data returning certain metrics, probably that is the right key for selection. Okay. So to apply parallelism, as usual, right, we need to set the completion parameters like max parallel workers and all this. And then you have to change the function definition to parallel safe. Yeah, so this is basically one function where we applied the parallelism, and I want to tell the limitations as well here. Right? So to apply the parallelism, so by default Postgres come with parallel unsafe. You need to make it parallel safe, and then then function will pick up the parallelism. But when you are invoking the parallelism, you see that there are certain limitations. For example, you cannot use the set statements. You cannot use, create template tables, adopt template tables. And when you are returning the result set back to the customer client, so even for the ref cursors also it throws error whenever it is returning multiple cursors back to the calling environment. So by applying this parallelism in our particular customer, we gain good performance on 5 functions where we leverage this parallelism. So the second use case, the CPU spiking code pattern at high concurrency. So this again falls into the same database context. So whenever basically it's a pre-production phase, we are we are basically testing the production load with Java. Okay, and we found that whenever one function is executing at high concurrency with 100 users, this is causing a high CPU on relatively 16 core large. And so when we look into the function pattern, why it is causing the high CPU. So before looking into the function, we have seen like all the metrics, do the nested analysis, still we can't figure out why it is happening, right? So we deep dived on the functional logic. If you look into the code, so focus on the if flag, right? If it is a if flag, it is checking exist condition on certain query. If that condition true, then it will hit another SQL. And again, there is one more branch, INT exist, checking on the certain SQL query for the indicator column, then hitting on the complex SQL. Okay. Like that, we have 6 branches. Okay. So this is the pattern we observed. So if you see, right, so if condition query is checking for exist, okay, basically on the indicator column, which is a low cardinality column. Okay. So such bitmap hit on 6 branches, hitting very frequently is the cause of the CPU we got when we basically spent a lot of time in analyzing the pattern using all the insights. So to fix this, so we know that the bitmap scan is the key for this. So we avoided bitmap scan first intermediately by changing the branching to the most frequent. For example, there are 6 branching conditions, right? So we know that which is the most frequent. We ordered to the most frequent to the top and reordered to the low, so that at least we get the most probability first, okay? And then we introduce a new lookup table to avoid the bitmap scan. So basically, right, so whenever you see performance issue, you can deep dive and look into the code pattern and you can resolve. This is one of the case which I want to. The third use case, so function with R conditional constant evaluation. Okay, so this basically is simple, right? Whenever you got a performance issue, right, you can, if you understand the business logic, application logic, right, there are simple ways you can resolve the problem. If you look at the function, so the function is passing a parameter with a constant, okay. If you see the cursor logic, right, so there is a cursor which basically checks for that parameter. If it is 1, then get the result. If it is not equal to 1, it is violating the date conditions. So if you understand this for each execution, the one is the constant, okay. So the developer in a legacy model, he coded together because, for example, in this query ordering condition, let's say rows coming to that here, every time it is evaluating the constant condition, which is unnecessarily, right? So to redesign this, what we did, right, we divided into the SQL query into 2 parts. The first one and second one, we basically, right, if it is a constant, we divided the first SQL based on the constant. If it is not, then we go by the dates. So with this kind of refactoring, we got the performance benefit from 2 seconds to under 1 second. So all these 3 use cases, right, we did not deep dive on SQL and query plan, getting the indexes and all these things. We looked into the application, we got the benefit from how the code got built and what are the options that is available in the procedural language. So Here I want to talk, lightning talk on this multivariate statistics, okay, which is a Postgres 15 release. So you know that statistics are important. So basically when you analyze or systematically gathering the stats, the planner make use of these stats and it will apply on the query plan for the efficient execution, right? So what is this multivariate stats? This got introduced in 15 release, right? So these are kind of extended statistics which you can build on interdependent columns. For example, in a table there are two columns which is a dependent data, right? So in that case, you can use up this extended functional dependency stats. So to understand this, so I have created a simple table with a uniform distribution. That test MPS is a uniform distribution with 100 rows divided basically 10,000 rows with 100 occurrences, 100 into 100. Okay. So now I ran the explain knowledge on this query. So basically select star from the table where column A equal to 1 and column B equal to 1. So make sure you remember, right, this table is a uniform distribution. So both columns have equal data and equal distribution. So when you run this query, right, optimizer by default think, right, each column is independent and it knows that there is a 1 in 100 unique value, right? It thinks that 1 by 100 probability, it estimates that there is one row is coming. But since it is a dependent column in the equal distribution, actually is coming as 100 if you see the rows. So the estimates are very different in higher magnitude. So obviously the execution plan also is not efficient, which by default causes performance. This is for the calculation. So optimizer thinks A and B column are independent. So it applies AND condition. You get estimates as a one row. Okay. So to solve such kind of interdependent scenarios, we have now option to use dependency stats in Postgres release. So what I did is, right, we have created statistics, functional dependency on column A, and then we did analyze. So basically now interdependent stats are available for the optimizer. Now when we execute this same SQL after this interdependent stats, now look at the rows estimated versus rows actual in the plan. Since now optimizer stats are know that it is equal distribution, rows estimated equal to 100, actual rows also 100. So obviously we get the better performance for efficient plan. So like this, we had most common values and end distinct interdependent stats available in Postgres 15, which you can make as the performance. So here the references and any questions. Sorry, I got an echo from God service. Yeah. So any questions?
Even can you talk about any other use cases apart from the 3 use cases? Any other use cases for extended statistics that you have bumped into recently?
Yeah. So end distinct use case. Basically, if you column having number of districts. So basically, you are running count of districts on the interdependent columns, right? So in that case, also you can apply the extended stats end distinct. So it will basically calculate the number of distinct values across 2 columns. It gives in the memory, which will supply for the execution plan. So end distinct is one, and there is a most common values also there. So it depends on the application, right? So when you deep dive on the what query, definitely these are the anchors for the performance. So why we go for the procedural language? Again, there are 3 anchors. So you can reduce the network overhead from client to server, and there is a memory intermediate sharing across SQL, right? That also you can avoid because you are traveling and sending back to the database server. Okay. And query parsing also not required. So if you see the procedural language, that is a powerful for your application when you think of a performance. So that's all I want to share.
Which type of data types we can use for extended stats?
There is no limitation to my knowledge.
So we work with that.
Yeah. You just have to prepare the stats before and that will be.
And obviously, you don't want to create statistics.
Yeah, unnecessarily. So you have to use caution. Everything, any performance, you need get a collection.
Right. If you guys remember about Silesh's presentation on default statistics target, right? So you would want to correlate between what Yugundhar said on that use case for statistics versus the most common values, right? There's a direct distinction between those two things.
Is there any difference between character varying and text column, right? Data type, the performance, right?
No, obviously, right? Text, it is a lot of, by default, the memory allocation is more. Text, where means you are giving certain memory, right? That's also matter. For example, you are inserting 100 rows. Text, row 100 rows, you are interested in 20 bytes, but text will allocate before 1 memory. Am I right? So, whereas if you define where to 20, it is allocate less memory. So, that's actually one key.
And compared to JSON, JSON B column?
Yeah. Compared to this,
so the operator class changes basically. So between your character varying and the text column, the operator family changes. So that's the whole structure of operator family, and then the operators, what is the exact operator to be used while you are trying to look at it as part of your where class. That operator class is what changes distincts between your
whenever we use it.
I've got JSON expert, as Thomas, Rajesh, if you have any questions on JSON, has done tremendous amount of job on JSON.
So I had a query. In first scenario, you used if-else if kind of logic. How do we define when to use switch case and when to use if-else kind of logic?
So how we
Based on what
we
we decide this?
That will help.
This one. So how I define the branching condition of this, right? So basically, as per business, we understand that there are branching conditions, right? So it's a equity application. Which condition will hit most frequently from the virtual point of view, right? So if we, let's say, there are 6 conditions, your fifth condition is most probable out of 100. Out of 100, it will go to fifth condition for 90, right? So if you are keeping that as a fifth condition, the first 4 conditions are valid for every time, right? Which is unnecessary, right? So if you know the business and which condition is most probable, if you keep that as a first branch, the first 90 will hit the first 90. Important point, right? The flow for the earlier is the first 90 hits has to traverse across 4. So 4 if conditions hit 90 times. Whereas if you reorder it, the first condition will hit 90 times, the rest are not hit. Because when it does it, won't go for other conditions.
Should I deduce that for smaller data sets or for smaller logics, we should use if-else, but if there is huge variations in the logic manipulations, we should stick to switch statements.
Yeah, that is one. But bitmap scan with a high frequency is a cause of ICP. We should avoid it. So that is one way intermediately. So we have introduced one for lookup table data instead of using this local automatic columns, and why don't you introduce a lookup table which matches this lookup data, right? That is a finite solution. But bitmap reads when we go for a high concurrency only, it is cause solution. If it is not high concurrency, you can't find it reliable. Only the pre-production only you find.
Thank you.